Ocean currents. We have a few key questions to look at. One is what causes them. Another is what are the global ocean current patterns? In other words, what's the global geography of that? And then finally, how do ocean currents interact with climates? And there's a nice, maybe 2 to 3 minute animation here to help you get started with that. And just have a look at that. I'm not going to play it here because the quality is lower of the audio. But what I would like you to understand in that is what the broad patterns are, what ocean gyres are, GYRES, and how the global winds and current patterns are similar, but not the same. There's a directional difference there that has to do with the Coriolis effect. So that's the introduction in that. Have a look at that, and then pick it up on the next slide here when you get done with that. Okay, so ocean currents are generated by surface winds. So we've been learning about those, so it's a natural time to come in and look at this. They're also generated, though, by differences in surface water density, which are due to either differences in salinity itself, in other words, the salt content of the water, and temperature differences. And if you combine salinity, haline has to do with salts, and then thermo is temperature, you get that sense of why we call them thermohaline. So basically, temperature and salinity induced circulations. And in all cases, almost all cases, the main driver is the water density difference itself. And we'll see that there are some huge differences in that. The other one that's really more minor, but can be important, is just evaporation and sea level gradients. And if I forget to mention that, the Mediterranean is a classic place where you see this happen. It's just a big evaporation pond, really, in the summer, and so you have a loss of fresh water out of the rivers that flow in the Mediterranean, and that loss of water is faster than the ocean, Atlantic Ocean out there. So you have a circulation of replenishment of Atlantic seawater into the Mediterranean that happens especially in the summertime. So that's an interesting one. The Sea of Cortez does a little bit of that for part of the year as well. The Baja Peninsula of Mexico, just inside that. If you are familiar with that area at all, one of my favorite places in the world. So surface currents generally flow, and as you saw in the animation in sub-basin scale, circulations is gyre. So, for example, in the North Pacific, if this is the North Pacific here, then this is the general direction. And it kind of looks like, gee, that's a clockwise circulation like we see with the high pressure cell in the area. And yes, they are similar. But Coriolis effect, just to remind you what you just saw, is something that changes that sum. So that Coriolis surface current differs up to 45 degrees from the overlying wind, and that apparent deflection is to what direction in the northern hemisphere and what direction in the southern. So remember that with the winds, it's to the right in the first, so it's the opposite for the southern hemisphere. Um, then also, we'll come to the next slide in a bit. The east margins of currents are cool for their latitude, and so we're on the east side of our ocean, right? Our west coast is the east side of the Pacific Ocean, and that is also true of the Humboldt Current of South America. Much of the west coast of South America is dominated almost all by the Humboldt Current, and the California Current is what we have here in the western United States. Some people would say, oh, California Current is the whole circulation from BC on down. I won't argue with that. But the point is, it comes from the north coast towards the equator. And then the Benguela Current of South Africa on their west coast is yet a third example. There's also a lighter one in Australia. Anyway, so those are cool for their latitude. So if you don't believe that, just go out to the Oregon coast and tell me that's not cool. That's a very cool place, right? For what you would consider. So it flows through what would otherwise be warmer water, basically, is how we define cool or not cool. And so the warm currents are on the other side of the continents. The Gulf Stream of the United States, we're going to spend quite a bit of time on that later. The Kuroshio Current, or Japan Current, sometimes it's called, and these flow toward the pole. So they bring warm water up into the colder northern oceans in our hemisphere. And so they have just the opposite. So they moderate northern temperatures enormously by bringing that tropical heat. Basically, the energy of the sun is brought into the higher latitudes, even the Arctic, by these northward flowing currents. Kind of an amazing thing. Huge heat exchange. It's not just winds that do that, but also the ocean currents help moderate the extremes, cool off the tropics, warm up the higher latitudes. Winds and ocean currents. Note that the ocean currents move to and just kind of remember this. We just went over that before. And the major gyres you see here, that's an ocean gyre. That's the Pacific gyre, the North Atlantic gyre. And you can see the opposite turning here. Thing to note here again is, yes, the wind is driving the current, but then the current goes off to a net transport of almost upwards of 90 degrees, depending on what level we're at. But even at the surface, it's 20 to 40 degrees or so different than the wind itself. So you have this interesting pattern where you have this big gyre system, and the actual movement of the ocean currents, even though they're driven by the winds, largely are not in the same direction because of the Coriolis effect and the Ekman spiral process, which you'll get a chance to look at a little later. So these are, if you were missing this, I should have shown you this first. Winds, the warmer currents, and the cooler currents. Okay, so you see the pattern. This is a more deluxe kind of, I love this map. There's just so much happening here, and you can see a high pressure center here and here that would be driving these currents, the winds that drive the currents, kind of thing. And look at this. Something interesting here. We look at this flow. We have this huge flow, wraps around, comes through here. Some of it's warm, as you can see, not very well done there. But you have literally heat from this ocean that goes all the way around here, flows out of the South Atlantic around here, and that heat, literally by the time all of this water comes through these very low latitudes, even equatorial latitudes, tropical latitudes, there's been a huge amount of evaporation and salinity. So we're going to later look at that question. And again, our cool upwelled, we're going to look at upwelling later, but our cool current coming from the north. So it's cool because it's from a higher latitude, as is these areas here are cool as their cool current is coming from a higher latitude as well. Oops. And also we have long distant immediate coast and near coast areas, a similar thing happening down here. These are zones of surprisingly cool temperatures. A little bit of that in northern Africa shows up on this map too. Okay. So this just shows you if you were to, have a cargo spill or a bunch of toys drifting, where would the toys end up? Kind of tells us something about ocean currents. It's kind of an interesting story. If you dropped a bottle with a message in it, where would it go in the whole story? So there's all these kinds of little experiments that when you find something that came from somewhere else, you go, hey, that's very interesting. Now, deep thermohaline currents are important in our story as they're great, great moderators of climates. And there's a very long involved one along the Antarctic coast here in the southern hemisphere. You can imagine Antarctica is here in this map. And you got cold water sinking here. They don't really show that here. But you also have an area here where, as I pointed out a few minutes ago, where the water is coming from this basically warm regions here, the equatorial Pacific and tropical Pacific, flowing around Africa, coming all the way up into the whole North Atlantic area. And there's some important things happening there. So those are deep thermohaline currents. Remember thermohaline, so temperature and salinity induced density currents. The water sinks when it's denser, and it can be dense because it's salty or because it's cold, or a combination of the two. And we'll look real carefully at that with some maps later on. So the next three slides set the stage to understanding causes of the deep thermohaline currents shown in the previous slide. Basic concept again, colder temperatures, greater density. Greater salinity means greater density. So if you want greater density, you either make it cold or saline or both. It turns out it's kind of hard to make it cold and saline. There's really only one place in the world where that happens. We'll get to that later, but it's not hard to make it cold. Just go to Antarctica, right? water that is both cold and saline is most dense. And so what I want you to do is look at the next slides is to look for the regions where both we get cold and saline. Okay. But emphasize something, salinity tends to be the strongest driver of density. So I would say, when you're seeing the slideshow without me talking, maybe you like me to be quiet once in a while, right? Would he ever shut up? Um, yeah, maybe I'd stop for a moment here, right? You guys are working hard. Those of you who are watching these shows, I know that you're spending a lot of time, and I am too. But I really hope that these help you in what you're doing. So I'm hoping that these narratives help you understand the slide. So let's go. Wow, beautiful slide. So we've got you don't have to even know have a legend here to tell you what's going on here. You can tell where it's warm and where it's cold. The dark blues are cold and so on, all the way up into the very warmest equatorial areas. So what then I also want you to consider in this is the surface salinity, and it's kind of intuitive that we would have a white color like salty color where it's more saline. And so some amazing stuff going on here. Wow, the Mediterranean, very salty. Yes, it's an evaporation area. Persian Gulf, Red Sea, these are areas as well that are very saline, not surprisingly. Pretty saline here for its latitude as well, the Baja, the Sea of Cortez here. And then it might surprise you how saline really much of the Atlantic is, much more so than the Pacific. And again, it's that partly because that wraparound current brings so much tropical water where there's been lots of evaporation, and that evaporation makes it very saline, and it circulates around all the way across the enormous spans of distance in tropical areas, many of them very, very dry. Like this is a very dry area here, and this is pretty dry usually off here as well. And so these circulation patterns are very saline water. You get to way up here. This is the only part of the world where this far north you get quite saline water. Kind of a remarkable thing. Okay, and not saline at all here though. Okay, and rivers. The resultant sea density, when you look at the temperatures and the salinity, is that you get some very dense waters in the Mediterranean. Now, that's not cold, so it's not temperature there, it's salinity driving that, right? But what about up here? Up here, we just saw that it's kind of saline for that. I mean, more saline than any other part of the world. Um, and it's also cold. So you have a very strong salinity driven pattern here, not so much along here. You might go back and look, right? So the salinity isn't really that strong here along Antarctica, and yet you get some really strong downwelling, sinking waters in these areas. Nonetheless, so it's temperature driven all the way through here, very, very cold along there. What's going on? So one of the things is when you have winds blowing over the surface, you can have some upwelling. But another thing is when you're forming sea ice, which does form along here seasonally, the sea ice forms into pure fresh water. And so the salt in the water gets exuded as the water freezes. So it makes it somewhat more saline here. But really, it's really largely just about being cold along a very cold part of the world. But up here on the other hand, we get pretty cold, but also saline. And salinity is really the story there. And so this is an area then of so dense, this is the density map again, that this is an enormous region of sinking water, very much so, driving the thermohaline circulation. All right. So I've got some stuff for you to look at here. This is basically a set of questions. I want you to think about these, and I'm not going to lead you to the answers with my narrative here. I want you to think real carefully about it. I have given you some clues the way I've talked about it, and I've also raised some questions here. So have a look at all of these questions, and I can guarantee you some of this will be on exam. So this is Pater. Definitely. And it's not terribly complex. I think you will be able to figure this out. And when I talk about the Baltic Sea here, by the way, don't despair. We've got a Baltic Sea region right down in here. Okay, so hopefully that will all make some sense as you look at it. We're going to have to come to coastal upwelling on another slide, or another show. So thanks for your attention, and we'll finish up this ocean current stuff in our next presentation.